Imagine a computer so powerful that it could solve problems in minutes, problems that would take today's fastest supercomputers longer than the age of the universe. Now imagine something even stranger. This computer doesn't look like a computer at all. Instead of a sleek box or a laptop, it looks like a giant golden chandelier hanging upside down inside a metal chamber. And here's the shocking part. This machine must be protected not just from heat, not just from vibration, but from the entire universe itself. Even a tiny whisper of energy, a single particle from outer space, or the signal from a nearby phone could destroy its calculations. So the question is, why is a quantum computer so fragile? And how are scientists trying to build one that can survive in a noisy world? Today, we're diving into the science behind one of the most ambitious technologies ever created. If you've ever seen a picture of a quantum computer, you probably noticed something unusual. It doesn't look like a normal computer. No monitor, no keyboard, no motherboard. Instead, it looks like a complex metal structure with layers of tubes and wires hanging inside a sealed container. This strange shape is not for decoration, it's for survival. Unlike classical computers, the laptops and phones we use every day, quantum computers operate under extreme conditions. A classical computer works perfectly in your bedroom, office, or classroom, but a quantum computer cannot. Because at the heart of a quantum computer is something incredibly delicate, the qubit. When most people hear the word noise, they think of loud sounds, shouting, traffic, construction. But in physics, noise means something very different. Noise is any random energy that interferes with a system. And in the quantum world, even the smallest amount of energy can cause chaos. Examples of quantum noise include cosmic radiation from space, background radiation from Earth, electromagnetic signals from phones, microscopic vibrations, heat, temperature changes. Even the natural movement of atoms can be considered noise. And this is a huge problem, because qubits are extremely sensitive. A classical computer stores information using bits. Each bit is either 0 or 1. Simple. But a quantum computer uses qubits, and qubits are very different. They can exist in multiple states at the same time. This phenomenon is called superposition. This is what makes quantum computers powerful, but it's also what makes them fragile. If a qubit interacts with its environment, even slightly, its quantum state collapses. This process is called decoherence, and once decoherence happens, the calculation is lost. To protect qubits from noise, scientists use several extreme measures. First, they place the quantum processor inside a vacuum. This removes air molecules that could interfere with the system. Second, they cool the processor to an incredibly low temperature, almost absolute zero. Absolute zero is minus 273.15 degrees Celsius. Scientists cannot reach absolute zero exactly, but they can get very close. Most quantum computers operate around 0.05 Kelvin. That is colder than outer space. At this temperature, atomic motion slows down dramatically, reducing thermal noise. But even after all these precautions, vacuum chambers, radiation shielding, and ultra-cold temperatures, noise still exists. It can never be completely eliminated, and this creates errors in quantum calculations. So to fix this problem, most quantum computers rely on error correction. But error correction requires a large number of extra qubits. Sometimes thousands of qubits are needed just to protect a single useful qubit. This makes quantum computers large, expensive, and difficult to scale. So engineers began asking a new question. What if we could build qubits that naturally resist noise? Instead of simply increasing the number of qubits, scientists decided to redesign the qubit itself. Their goal was simple:
create a qubit that could survive in a noisy environment. And their solution came from a surprising branch of mathematics, topology. Topology is the study of shapes and how they can change without losing their essential properties. For example, a coffee mug and a donut look very different, but in topology, they are considered the same. Why? Because both objects have one hole. You can reshape a mug into a donut without creating or destroying that hole, so their fundamental property remains unchanged. This simple idea became the foundation of a new type of quantum bit, the topological qubit.
To understand how topological qubits work, scientists needed to explore a very unusual idea, the idea of a particle that could be its own opposite. In normal physics, every particle has an antiparticle. An electron has a positron. A proton has an antiproton. When a particle meets its antiparticle, they destroy each other and release pure energy. But scientists once proposed a strange possibility. What if a particle could be its own antiparticle? This idea was first suggested in 1937 by an Italian physicist. The particle was later named the Majorana particle. For decades, this particle remained theoretical. Scientists searched for it in laboratories around the world, but detecting it directly proved extremely difficult. Eventually, researchers discovered something fascinating. Even if the particle itself could not be found, its behavior could be recreated, not as a real particle, but as something called a quasi-particle. A quasi-particle is not a fundamental particle. Instead, it is a collective behavior of many electrons acting together as if they were a single particle. This discovery opened the door to a new type of quantum technology. Scientists realized that if they could engineer the right combination of materials, electrons inside those materials could behave like Majorana particles. And that is exactly what engineers attempted to do. After many years of research, a new kind of quantum chip was developed. This chip used a special structure built from carefully selected materials. One material acted as a semiconductor. Another acted as a superconductor. When these materials were combined in a precise atomic arrangement, they created a completely new environment for electrons. Inside this structure, electrons moved in a coordinated way. Their collective behavior formed quasi-particles with topological properties. And this is where the real breakthrough happened. Instead of storing information in a single fragile location, the system stored information across two separate points. One part of the information existed at one end of the structure, the other part existed at the opposite end. These two ends remained connected through quantum physics. This created a natural protection mechanism. If noise disturbed one end, the other end still preserved the information. In other words, the information was distributed rather than localized. This distribution made the system far more resistant to noise, and resistance to noise is the single most important requirement for building reliable quantum computers. Today, many companies and research laboratories are racing to build better quantum machines. Some focus on increasing the number of qubits. Others focus on improving stability. Both goals are important, but stability is often considered the bigger challenge because 1 million unstable qubits are less useful than a small number of stable ones. Another major breakthrough came from improvements in error reduction. Modern quantum chips are becoming better at detecting and correcting mistakes. In recent experiments, advanced quantum processors have demonstrated the ability to perform extremely complex calculations in a very short time. Tasks that would take traditional supercomputers an unimaginable amount of time can now be completed in just minutes. This does not mean quantum computers will replace the computers we use every day. Instead, they will be used for very specific problems that require massive computational power and extreme precision. For example, simulating chemical reactions,
designing new medicines, developing advanced materials, optimizing complex systems, predicting climate behavior, modeling weather patterns. These are problems where classical computers struggle to keep up, because as systems become more complex, the number of possible outcomes grows exponentially. Eventually, the calculations become too large for traditional machines. Quantum computers offer a completely different approach. They use the laws of quantum physics to explore many possibilities at the same time. This ability could transform fields like medicine, energy, artificial intelligence, and environmental science. But the journey is still in its early stages. Quantum technology is one of the most challenging engineering problems ever attempted. It requires precision at the atomic level. It requires temperatures near absolute zero. It requires protection from even the smallest disturbances, and it requires entirely new ways of thinking about computation. Yet progress continues. Every year, researchers move one step closer to building practical quantum machines, machines that could solve problems once considered impossible, machines that could reshape science, technology, and the future of humanity. The quantum revolution has already begun, and the next breakthrough may be closer than we think.